Okay, so in this video, we're going to go through some specific examples of covalent shapes, how to draw the Lewis dot structure, how to draw the shape structure, how to properly name it, how to identify the polarity. Just a quick note for people who are viewing this video who aren't currently enrolled in my honors class. Sometimes this is one that people in college chemistry, randomly you will find on YouTube. And it's important to know that these are examples for high school honors chemistry. So as such, you're not going to see any of examples of the expanded octet shapes. And those of you in my class that are like, what is she talking about? Don't worry about it. But for the college folks that kind of find this video accidentally, I am not going through any of the expanded octet. So you're not going to see any of the seesaw or the trigonal bipyramidal in this. This is strictly non-expanded octet shapes. So just the basic shapes. If you are looking for that as a video, this one is not going to cover it. I'm very sorry. I do not have a video currently with those expanded shapes. I will work on that one day. Today is not that day. Okay, so getting into these, we're going to run through how to, if I give you just a compound name, what do I do with it? How do I come up with the various parts of the answer that I might be asking for? So first thing is you will either be given a name or a formula. And because we've already covered nomenclature, if I give you the name, you can come up with the formula. I can ask you for a Lewis structure. So again, what does a Lewis structure mean? Remember that a Lewis structure means I need to see dots. And remember that those dots represent electrons. So anytime you see the word Lewis or Lewis dot, you need to show electrons. You're not going to show them as a line. You're going to actually show all of the individual electrons. And remember that the Lewis structure shows the electrons and how the electrons are being shared. It does not necessarily represent the shape. Okay? The shape model and the shape name, what is the three-dimensional geometric shape that these compounds actually take on, and how do I name that? And then based on the specific compound, what's the polarity? We have talked about the general polarity of these compounds, or I'm sorry, of these shapes, but depending on the elements that you have, some of that can go out the window, and I'm going to show you some examples. All right, so let's just go ahead and get started. We're going to jump right in with boron trichloride. So the first thing that I would do with boron trichloride is I need to write the formula. I need to see what elements I'm working with and how many of each element I have. So boron doesn't have a prefix. I know that means I have 1. And trichloride, tri is 3. I've got 3 chlorines. So I've got 1 boron and 3 chlorines. Now, I need to figure out what's in the middle. When I'm looking at what's in the middle, you need to think about how many bonds these things can make. Right? Boron has the ability to make 3 bonds. Chlorine has the ability to make 1 bond. Okay, chlorine can't be in the middle. Boron has to be in the middle. The boron's bonded to 3 chlorines, so it only makes sense that boron's in the middle. So when I draw my Lewis structure, I'm going to start with the Lewis dot diagram of boron, which has 1, 2, 3 electrons. And I'm going to switch colors of pen here. You don't necessarily have to do that on your assignment. I'm doing it just for clarity so that you can see it. So I know that boron has 3 electrons. I know that chlorine in the 7A column has 7 valence electrons. So I'm going to start filling in my electrons for chlorine. So 1, 2, 3, 4, 5, 6, 7. And see where we have the red dot and the blue dot? That would be where they are bonded. That would be my covalent bond. Notice that I have no more than 2 dots on any given side. Okay. And so that is my Lewis dot structure for boron trichloride. I'm going to zoom in on that just a little bit so we can see it a little bit better. Okay. Boron, because it only has 6 electrons, has not satisfied the octet rule, but chlorine has. Chlorine feels like in all its valence shell that it has 8. Okay. And boron is an element that can be stable while simultaneously not having a full octet. All right, so with boron in the middle, we know that boron forms a shape that's called trigonal planar. So now I'm going to draw that shape. So I'm going to put my boron in the middle. and I'm going to draw the 3 bonds, and I know that they are at characteristic angles due to the electron repulsion, and then I'm going to fill in my chlorine. Well, remember that the bond here is essentially taking the place of the red and blue dot, but I still have to draw the rest of the valence electrons that exist around the chlorine. So there are 6 additional electrons outside of the red and blue dot. So I'm going to draw my 6 valence electrons. And I know, because I've already done the Lewis dot diagram, that they are paired. So I'm just going to go ahead and put them in that way. All right, and so again, there's my shape. We know it is trigonal, planar is the name, and then the polarity. Okay, we'll think about what's happening here. The chlorine in each of these bonds is exerting equal pull against the other in the tug-of-war over the electrons. They're all being pulled equally in all directions. So this is a nonpolar molecule, so NP. Okay. All right, let's go on to our next example. So phosphorus tribromide. So phosphorus, P, tribromide, Br3. All right, consider again what's probably in the middle. It's probably going to be the phosphorus because bromine as a halogen can only make 1 bond. Phosphorus in the 5A column has a pair of electrons and then 3 single electrons, so it can make 3 bonds. So it's probably in the middle. So I'm going to draw my phosphorus and its Lewis dot diagram. 5 valence electrons, 1, 2, 3, 4, 5. And remember, it's very important that that unshared pair of electrons is on top. Okay, and then I'm going to draw in my 3 bromines. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. No more than 2 on any side. And then again, the red and blue dots, that shows me where my bonds are. Now I'm going to draw this as the shape model. Phosphorus in the middle, unshared pair of electrons on the top. Remember, that indicates what I'm seeing with my shape. Okay, and we see that this is forming a pyramidal shape. Okay, pyramidal shape. And because I have that unshared pair of electrons on the top, this is going to have a polar characteristic. All 3 of these bromines are going to pull equally on the electron in the bond with the phosphorus, but this unshared pair of electrons has a strong pull. And so we're going to actually see that there is a polar moment with this unshared pair of electrons. Okay. All right, next one, carbon tetrachloride. So carbon tetrachloride, C for the carbon, tetra is 4, chlorine, so CCl4. So again, what's going to go in the middle? Well, carbon's going to go in the middle. Carbon can make 4 bonds. Chlorine can only make 1 bond. So I'm going to put my carbon in the middle with its 4 valence electrons. And then I'm going to fill in my 4 chlorines. Hopefully we're now kind of seeing a pattern of how these are laying out. You're always going to have an element bond where you have space, where you have an open valence electron spot. Okay. So carbon in the middle, carbon made 4 bonds, tetrachloride, that should remind you we're making a tetrahedral shape. So carbon, 1, 2, 3, 4, and then our 4 chlorines, Cl, 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 Cl. Okay, and that shape again is tetrahedral. And then consider your polarity, right? This chlorine and this chlorine and this chlorine and this chlorine, aren't they all pulling the same? They're going to have the same electronegativity. Carbon has the same electronegativity. The electronegativity difference between these elements is all going to be the same, so it's nonpolar. Okay, so let me show you a variation on this. What if instead of CCl4, what if I changed it to be CH3Cl? So in this case, my carbon is bonded to 3 hydrogens and a chlorine. So let's draw that one out. It's still making 4 total bonds. It's still going to be tetrahedral in shape, but think about your pull of electrons. Is the chlorine going to pull the same as the 3 hydrogens? No, because chlorine has a very different electronegativity value. So it's still tetrahedral in terms of the shape. But this one, because it's not symmetrical in terms of the pull of the electrons, would actually be polar. So those are the kind of things you're going to have to watch out for. It's not just what the general polarity of the column is. You have to consider what's bonded to the element in any given example. So carbon tetrachloride, CCl4, tetrahedral shape, equal pull in all directions, nonpolar. CH3Cl, tetrahedral shape, but polar because I don't have equal pull in all directions. Okay. All right, next one. Silicon disulfide. So silicon is under the same column as carbon. So tetrahedral shape? Maybe. Let's look at what the actual formula here is. So silicon disulfide, Si, di is 2, S2. So silicon in this case is not forming 4 bonds. It's not bonding to 4 things. It's only bonding to 2 things. If it's only bonding to 2 things, and I know I normally make 4 bonds, there's a good indication that I'm going to have a multiple bond here. So I'm going to walk you through how to determine that. You're going to start by drawing your Lewis dot structure, starting with your silicone in the middle. We're going to start with silicone in the middle because it makes the most number of bonds. So Si, 1, 2, 3, 4. And then I have 2 sulfurs. I'm going to put 1 on each side. Okay. And each sulfur is in the 6A column. It gets 6 dots. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So, I smeared the pen a little bit. Sorry, guys. This is a dot, not a smear. So these 2 electrons and these 2 electrons are already paired up. Same thing with these 2 electrons and these 2 electrons. And it should make sense that these 2 are going to join together and make a bond, and these 2 are going to join together and make a bond. But what about this one and this one and that one and that one? We can't just leave them out there. They have to be paired up. So what we actually see is that these rearrange themselves and come inside and make a double bond. So I'm going to redraw this cleaned up so that you can see it cleaned up. But sometimes it's not super obvious to begin with what I'm going to end up with. And you have to go through that process that we just did where I start with my elements in a certain position and I might have, or my elements, my electrons, and I might have to rearrange them a little bit. Okay. And so if we look at this, both silicon and sulfur feel like their octet needs have been satisfied, right? So silicon feels like it has 1, 2, 3, 4, 5, 6, 7, 8 electrons. And sulfur feels like it has 1, 2, 3, 4, 5, 6, 7, 8. And over here, 1, 2, 3, 4, 5, 6, 7, 8. Everyone is satisfied with the octet rule. And obviously, what I just drew was not a tetrahedral shape. Like this in no way looks the same. We've got double bonds. Anytime we have double bonds, it's going to force us into a linear arrangement. So the silicon in the middle, double bond, sulfur, sulfur, unshared pairs on the sulfur. Okay. And it doesn't matter at this level if they're top and side or top and bottom or side and bottom. As long as they're on there, I'm going to be pretty happy. This is a linear shape. And then think about your polarity. The sulfur pulling, the sulfur pulling. Even though there's unshared electrons here, right, they're exactly balanced out. This is like two identical twins fighting over the electrons. So this is going to be nonpolar. Okay. All right, so we got a couple more examples we're going to hit. All right, our next example, dihydrogen monoselenide. So what's our formula? Dihydrogen, di we know is 2, mono is 1. So this is H2SE. Probably looking at putting the selenium in the middle, right? Selenium is in the 6A column under oxygen, has 6 valence electrons. So 1, 2, 3, 4, 5, 6. And then hydrogen in the 1A column has 1 valence electron. H. Okay, so that's our Lewis dot structure. Again, remember Lewis dot showing all the electrons. Let's get our shape structure. So the selenium is under oxygen. That column demonstrates bent geometry. So I'm going to put my unshared pairs on the top. I'm going to draw my bond, and I'm going to fill in my hydrogens. And we see that that shape is bent. In terms of polarity, because I have my 2 unshared pairs here, those unshared pairs are going to pull way more than these hydrogens do. And so we're going to have a polar characteristic. Okay. So we got 3 more. So the next one we're going to look at is bromine. Well, bromine and what? Bromine isn't bonded to something? Well, remember in the previous recording I talked about how the halogens like to bond with themselves? Well, when bromine bonds with itself, I don't call it dibromine, right? It's just 2 bromines together. It's just bromine. So my formula here is Br2. Anytime you have the element and it's just its name, you have to assume it's bonded to itself. So we're going to see the same thing down here when we do this one for phosphorus in just a second. So let's talk about bromine. Bromine's in the 7A column. It has 7 valence electrons. Miss Stein messed up. Let me cross this out because I didn't draw this in a location that was going to be really easy to make 2 bromines come together. So let's do this. That's my bad. Do over. All right, there's 1 bromine with 7 valence electrons. It only has 1 open spot to make a bond. So when it bonds with my second bromine, okay, they share that 1 pair of electrons there. My shape diagram is just going to be bromine bonded to bromine in a straight line. And if it's in a straight line, it is linear. In terms of polarity, because bromine here is bonded to itself, can't be more electronegative than yourself. You can't pull harder on the bond than yourself, so this is nonpolar. Okay, we're going to contrast that with this next one down here, which is hydrogen monobromide. So hydrogen monobromide, HBr. So think about this. Hydrogen in the 1A column can only make 1 bond. Bromine in the 7A column can only make 1 bond. They can each only make 1 bond. What do we imagine the shape's going to be? It's going to be linear. It's the only option. So here's my hydrogen with its 1 electron, and then my bromine with its 7. Okay, there's my 1 shared pair of electrons. If I draw it in the shape structure, still in a straight line, linear. Now let's talk about the polarity. Well, here you can obviously, the bromine pulling on the bromine is going to be the same. But do you think the hydrogen and the bromine pulling on each other with the bromine having these extra unshared pairs of electrons, do you think that's equal? Heck no. So this is actually going to be polar. Okay. All right, our last one here, phosphorus. So again, we said if we only see the name of the element, we assume probably bonded to itself. So P2. All right, so phosphorus is in the 5A column, and the normal shape of that column is pyramidal, which the phosphorus would be in the middle with the unshared pair on top and then 3 bonds. Well, I don't think P2 is going to make 3 bonds. So if I don't know what I'm doing here, I don't know what direction to go in, I'm going to start off by drawing 2 phosphorus electron dot diagrams. and see if maybe I can figure it out by manipulating my electrons around, kind of like I did with that silicon disulfide on the previous page. So phosphorus, 1, 2, 3, 4, 5. Phosphorus, 1, 2, 3, 4, 5. Okay, so I can kind of see, I bet these two are going to bond. All right, well, if these two bond, can I bring these two up and make a pair and these two up and make a pair and satisfy everyone's octet rule? So think about it. I'd have 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. That doesn't satisfy everyone's octet rule. So if I can't satisfy everyone's octet rule by doing that, odds are I probably am going to make another bond. So I'm going to bring that electron up and this electron up and share here. Now, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I'm getting closer. Well, if a double bond didn't work, try a triple bond. So bring this guy in, bring this guy in, triple bond. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So let me rewrite this so it doesn't look like a hot mess. So phosphorus with the unshared pair on top, 1, 2, 3 bonds. 1, 2, 3, phosphorus unshared pair on top. So I have a triple bond. Is this pyramidal? No, sure doesn't look like a pyramid. Looks like a straight line. It's linear. Anytime I've got a multiple bond, no matter what the normal column would be, it's going to force it to become linear. So this is linear, and tug of war against yourself, nonpolar. Okay, so hopefully that's enough examples to at least get you started looking at the different shapes. Remember the key things. You know the general shapes of the columns. If the general shape doesn't help you out, start with the electron dot diagram. You might have to move some things around, but you're not going to see any of the more exotic type shapes in honors level chemistry. So this should get you going.